I'm here with Montgomery. He's going to talk about the sensitivity of simulated supercell thunderstorms to horizontal grid resolution. And Montgomery, can you just give me a overview on this research?
The main motivation for this project comes from the Warn on Forecast initiative. The idea is that we want to be able to make our warnings based off of a model output and not based off of radar detection or somebody spotted it on the ground. We know from previous research that being able to run at a high resolution is just not going to be possible, so we wanted to be able to consider certain things like grid spacing, the size of our ensemble, how complex our parameter schemes like turbulence or microphysics in convection allowing models. And so the first thing that we did that was different than other research projects was we initialized our model with a storm after about 30 minutes. So we ran a high resolution storm out 30 minutes, and then we used that as input into models at coarser grid resolutions of 1, 2, 3, 4 kilometers, and then ran that out for 90 minutes. We did that because in a real life situation, it would take quite some time for the radar data volumes to be assimilated into the model, and so we would usually have a developing thunderstorm by the time it got ran. We then did something interesting that hasn't been done in other research. We not only compared to the truth, we also filtered out the truth to different resolutions, so that way we could compare similar structures. So I wanted to, you have extra information. Let's see if we have a good truth. There's a whole bunch of noise there. We wanted to be able to get rid of that noise and make sure that we were comparing similar structures. We used 3 different model environments that allowed us to see a whole spectrum of supercells, wide varieties of CAPE, ranging from 1700 joules to 4600. We used different storm relative velocities. These also got changed throughout the process once we stumbled upon different results. We found for one of our environments, the Del City, the 4 kilometer didn't make it to the end. We found, interestingly enough, in the El Reno case, we had the 4 kilometer didn't spin up fast enough. And due to the fact that it took so long to spin up, it caused the storm not to move as far right. And you can see that after about 70 minutes, the 4 kilometer storms, 14 to 15 kilometers displaced from the truth. That's no good if you're trying to give somebody a forecast. And ultimately, we tried to summarize all these results into something that we call grid convergence plots. You take a time average ratio of the coarser output to the truth value, and the idea is that the faster it converges to 1, the faster the solution's converging to at least what we considered the truth. And so you can see here for one of our soundings, it ended up doing very well. El Reno was slightly, didn't do as well, and Del City did absolutely horrible. Mm-hmm. We ended up finding out that even though we changed the sounding so much, it took, we had to completely change the mid-level moisture and temperature profile, and we found out that, in this particular case, it was the size of the feature. The updraft was literally large enough that at 4 kilometers it was getting marginally resolved, but still better resolved than in the other soundings. And then finally, the horizontal vorticity. We found that there was issues in not only where the intensity showed up, but for how long. And so that created this conclusion that we came to, that even at 1 kilometer, when we compare it to the truth, we're still going to have issues when it comes to tornado forecasting. And ultimately found 4 kilometer was unreliable. It died, took too long to spin up. But you can see that at least quantitatively, 3 kilometers fared much better. So that's some good news. But another big problem that's going to stop us from being able to use these results is the fact that as we change the environment, we got dramatically different sensitivities. And final, but I haven't showed it here, we did try to change the initial conditions by making them more coarse, and it ultimately didn't severely impact the outputs, which will be good because we have a very coarse observation network currently.
Interesting. And where do you go next in this research? Do you have are there any other plans in place, or?
We were able to finish it and publish it in the monthly weather review. I don't have it here, but we did turbulence testing. We did a couple of turbulence parameterization schemes. We changed some of the microphysics schemes. We changed all of these soundings around by introducing more moisture, taking out moisture. We did a whole bunch of investigation into initial conditions. But as it stands right now, we won't put any more time into it. But I suppose perhaps you go to maybe finer resolutions. Maybe you try even more parameterization schemes. But I think the biggest result here is that it's not the same. The environments are going to change our ability to be able to say one overall goal, because the goal was, if, like for example here, if we saw that systematically this was 15 kilometers off, then when we get the ensemble output, I could know as a human, okay, this model output's usually 15 kilometers off, so I'm going to account for that. But it's not an overall result, so ultimately kind of left nowhere. It's results, but essentially just ask better questions.